Okay, so this is for the distinct imaginary root expansion problems that you encounter in lump parameter circuits. You'll know that you'll have distinct imaginary roots because your equation is going to have the form of this bottom quadratic here, where C is going to usually be much bigger than B or close to it. And what that's going to do is that when you actually carry out the quadratic formula, when you have B squared minus 4AC, this quantity under the radical becomes negative, and that's what gives you an imaginary number out front. So if we expand these terms, we now get something of the form of S and one pair and then S and the other complex pair, where the values of the quadratic formula now fall out to be an alpha and a beta. Now we use J here to denote the complex format instead of an I, because in electrical engineering we use I frequently. However, it's not a big thing here. We'll use I's for the actual computer calculator entry. So the conjugate over here is just going to be a plus, while this one remains a minus. Now to solve this, we would break this into its two component parts added by some undetermined coefficients on top. This is a general Calc 2, Calculus 3 method for determining a lot of integrals. Now once you have this set up, you can evaluate these where it makes these bottom terms go to 0. So if you wanted to find K1, you would plug in and evaluate this whole equation where you would have a minus alpha plus a j beta. So whatever gets rid of that. And as we can see up here, we have K sub 1, the one on top, is going to be equal to K, your original equation on top, divided by S plus alpha plus j beta. And then again, we're going to evaluate that now at S equals negative alpha plus j beta, the term that made this go away. Now when we do this, that gives us our K1 constant, and then we just plug it right back in, and that is our undetermined coefficient now. We know that K1 is also equal to K2 conjugate just because of the way complex pairs work. So once we get all that information, you can just take the inverse Laplace of this and you're done. That'll give you the format. There is a specific format that these follow, and it's 2 times the absolute value of K1 once you go through it. But I'm just going to show you how to find the K1 and K2 values here. So once we go over to the actual calculator portion of the video, you need to make sure that you have your calculator set to real for the complex format. You can find that in your mode settings. It's just a few levels down. But to get started, this is just going to be the equation, and then I'll show you how to actually type this in, but I'm just going to walk you through really quick. So you're going to start with complex solve, and that's going to take care of the fact that we have imaginary numbers in the system here. But you'll start your parentheses. Now, in computer language, square brackets denotes a subscript, so this is actually K sub 1, just looking at it. It's the exact same as this, just in computer formats. So K sub 1 equals your original K function over all of that. But you're literally verbatim just going to type in alpha K divided by, enter all that mess, and then you're solving it for K sub 1 again. Now the cool thing that you can do is you can now chain variables and label them all. So now you would press that with button, S equals that same equation that would set this equal to 0, and that's how you solve this again. But alpha, if you recall, is actually just the first term that falls out of the quadratic formula here, and you want both of these to remain positive, and I'll actually explain beta here in just a second. But alpha is going to be b over 2a, where b was this first term, a was this term, and that will actually be part of your later parameters. But right now, we're just going to have that, and then you chain it again with the word and. You're going to end up with beta is the square root of the absolute value of b squared minus 4ac. Now this is important because if you don't do the absolute value here, what ends up happening is you can end up with a negative number here, that'll get square rooted, and you end up with another imaginary number. So when you plugged in beta, it would say, yeah, beta is equal to imaginary something. It plugs it back into here, and that imaginary is canceled, and you're left with a negative result, which is undesirable. So you have to make sure that stays positive. You square root that and put that over to A. Once you have all of this in, you're going to store it as whatever function you decide as a function of your original K parameter, A, B, and C. You'll close that parenthesis, and then you're going to have it in your calculator. And then anytime after this that you want to solve the problem, all you will have to do is just recall that variable that you picked, start the parenthesis, you're going to type in the original K function, your A, your B, and your C. You'll hit enter, and that'll give you K1. And then you know K2 is simply just going to be the conjugate. And you'll be good. Okay, so now to actually put that into the calculator, you're going to have your original headings here. You're going to go under algebra, and then you're going to go down here to csolve. That's how you're going to start this, so it's going to open up the parenthesis for you. So now you can literally just pick on alpha, and then K, and then like I said, you start the square brackets, and this now denotes K sub 1. So K sub 1 is going to be equal to the original K divided by the quantity of S plus, and now you can do Greek characters in here. You just do second character, and that'll have Greek right there. So alpha is the first one. I'm going to do that plus second I times second characters, go back to Greek. I'm going to pick beta. Now this is just to keep all of the actual letters straight. I mean, you don't have to use Greek letters, but it does help in the final equation when you're trying to debug it if anything's going wrong here. So you're going to close off that parenthesis, and now you are solving for K sub 1. So again, alpha K, square bracket 1, end bracket, and finish off the csolve. Now, this is the cool part where we chain it. So now we hit the with button right here, the straight up and down bar. So that now means with, and here we say S is now equal to minus characters, grab our alpha again, plus I times beta, and then just grab beta again. We can now chain that second piece by going second and pressing the custom button, and that's going to bring up our new menu over here. So under solve, you can then say and. You could even type this out if you want, but it's just quicker to do this. You now say alpha is equal to B divided by, pressed the wrong one there, alpha B. Sorry about that. Alpha over 2A. 2 times A. Don't need that. And then you chain one more, and you just say and again. And now you go back, you grab beta, and you set that equal to the square root. And now you can do the absolute value. If you go into your catalog and look up A, that's the very first one for absolute value. Now you're going to do beta squared. Make sure we're still getting that on the camera. Beta squared minus 4 times A times C. Close that parenthesis and close the outer parenthesis, and now all of that is divided by 2 under parentheses times A, just to make sure we get it right. So now all of that is in there. At this point, you can hit enter. It'll return an error value. All it's going to do is just give you confirmation of what you're looking at, and it's just going to be this great big ugly thing. And it'll actually try its best to solve it, even symbolically, which is really cool. But at this point, so you have your K1 is equal to K over S plus alpha. I'll get that in a better look for you. Yeah. So we have csolve is K1. We have that original K over all of our stuff, solving for K1, where S is now equal to minus alpha plus I beta, and alpha and beta equal their respective pieces. So you can see where we have the absolute value surrounding that inner term to make sure that we don't get that extra I. So now, at the end of all of this equation, what we now do is we hit the store button, which gives us this little arrow. And once you do that, you now pick any function that you want. So this is distinct imaginary root expansion. I'm just going to say, how about something unoriginal? We'll say cROOT, where we have OOT. Now cROOT is a function of alpha k. I mean, just press alpha and then k. A, B, and C. So now anytime you want to recall this function, you're going to simply type out whatever you named up here. I mean, you could do anything up here. You could just say this is T of all of this, or you could say B of all of this, or anything that you choose. I recommend staying away from X, Y, Z, T, the normally commonly used things. You can even use like theta or phi on here, I think. But this is the simplest way to go about it. I mean, name it something that you know you're going to use, and then you can find it later if you look at one of my other videos on how to do this. And then once you have all of that, you just hit store. It'll return done. So now, if you're faced down with a problem that looks just like this, you're going to have that first K term, which you're going to put in as the first parameter. You're going to have your A, your B, and your C. And this will give you K1, and then you know K2 is just going to be the conjugate. Now really quick, I'm going to show you